Thermodynamics is the fundamental science that studies energy, its transformations, and how energy relates to matter. This field helps us understand how energy moves and changes form in the world around us. Energy is defined as the capacity to do work. It exists in many forms and can flow from one object to another. Think of energy as the fundamental currency that powers all processes in the universe. Heat is energy transfer that occurs due to a temperature difference between objects. Heat always flows from hot objects to cold objects, never the reverse, unless work is done on the system. Work is energy transfer that occurs when a force causes an object to move through a displacement. Unlike heat, work is an organized form of energy transfer that can be completely converted to other forms of energy. A thermodynamic system is the specific part of the universe we choose to study. Systems are classified based on what can cross their boundaries. Open systems allow both matter and energy to flow across boundaries. Closed systems allow only energy transfer. Isolated systems allow neither matter nor energy to cross their boundaries. Thermodynamics has crucial applications across many fields. In engineering, it helps design engines, refrigeration systems, and power plants. In chemistry, it explains chemical reactions and phase changes. In biology, it describes metabolic processes and how living organisms use energy. Understanding thermodynamics is essential for advancing technology and understanding natural processes. The laws of thermodynamics form the fundamental principles that govern all energy-related phenomena in the universe. These 4 laws provide the foundation for understanding how energy behaves in all physical and chemical processes. There are 4 fundamental laws of thermodynamics. The 0th law establishes thermal equilibrium. The 1st law governs energy conservation. The 2nd law describes entropy increase. And the 3rd law relates to absolute zero temperature. The 1st law of thermodynamics states that energy cannot be created or destroyed, only transformed from one form to another. This is expressed mathematically as delta U equals Q minus W, where delta U is the change in internal energy, Q is heat added to the system, and W is work done by the system. A perfect example of the 1st law is a battery powering a light bulb. The chemical energy stored in the battery is converted to electrical energy, which then becomes light and heat energy in the bulb. The total amount of energy remains constant throughout this conversion process. The 2nd law of thermodynamics states that the entropy of an isolated system always increases over time. Entropy is a measure of disorder or randomness in a system. This law explains why certain processes occur spontaneously in one direction but not the reverse. Entropy can be visualized as the degree of disorder in a system. On the left, we see particles in an ordered, low-entropy state. On the right, the same particles are in a disordered, high-entropy state. Natural processes spontaneously move from order to disorder, increasing entropy. The 0th law establishes the concept of thermal equilibrium and temperature measurement. It states that if 2 systems are in thermal equilibrium with a 3rd system, they are in thermal equilibrium with each other. The 3rd law states that the entropy of a perfect crystal approaches zero as temperature approaches absolute zero. These 4 laws of thermodynamics form the complete foundation for understanding energy behavior in the universe. They govern everything from the operation of engines and refrigerators to the evolution of stars and the ultimate fate of the cosmos. Together, they provide the fundamental principles that explain how energy flows and transforms in all physical processes.